Welcome back, everyone. This video is section 4.6, second part, that is on exponential growth but with relative growth rate. The model is a little bit different, but it inspires from the previous model that we learned. So with relative growth rate. So this model is very efficient for either predicting the size of the population, or if you have to compare different rates of population growth, or also expressing models, because we use the model here to be base 2, unlike the model that we used in the previous video was of base 2. So here we use it to base E. I'm sorry if I said 2 again previously. So it is we already used exponential function with base 2 to model the population growth. So when it came to in terms of the doubling time, but we also use the model, we could also use the same model for calculating, not the same model, a model to calculate the population with an exponential base with 3, also with base E. So if we use base E, we get a population model in terms of relative growth rate. So that is the difference between a model which uses relative growth rate and a model which uses doubling time. Okay, so the rate of the population growth expressed as a proportion of the population at any time. So in this case, R, which is the instantaneous growth rate, So in calculus, what do you mean by instantaneous rate? It means that at a particular instance. For example, if we have R is equal to 0.02, so then at time t, at any time t is t, the growth rate is 2%. 2% of the population, 2% of the population at time t. So if we have to discuss the model, or to define the model now, so the model for exponential growth we using relative growth rate would be a population so it can be stating the model or defining the model. A population that experiences exponential growth increases according to the model. In higher classes, you will learn how to model this, but here you are given a model already in hand. So what you have to know is, you have to just by heart these models and know the difference between using the doubling time, and based on the data that is given to you, use a model accordingly and solve the problem. So that is what you have to do, because you do not know how to frame this model, because that is not part of pre-calculus, so that is a part of higher level mathematics. So you just have to know the model that you use, that these are like kind of formulas. So you have to know the formulas and know which formula to be used for what data that is given in the problem, and use a model accordingly. So n of t is equal to n naught e to the power of rt. Okay, where n of t is nothing but population at time t. Population at time t. N naught is initial size of population. R is, as discussed above, relative rate of growth. and expressed as a proportion of the population. So and T would be the time. So you can notice that the formula for population growth is same as that for the continuously compound interest, correct? In fact, the principle works similarly for both the cases. So the growth of population per time period is proportional to the size of the population. And a population say of 1 million will increase more in 1 year than a population of 1000. So in exact same way, we have an investment of $1 million which will increase more in 1 year than an investment of $1000. So we will see how to apply this particular model to solve problems. Okay, so I will do an exercise problem for you. Say problem number 6. Okay, so I will read out the problem, the population, and chalk out the data that is given. The population of a certain species of fish has a relative growth rate of, so R is 1.2% per year. So it is estimated that the population in 2010 okay, 2010 was, what was the population? The population was 12 million. Okay, the population was 12 million. Find an exponential model n of, so first problem is A. Find an exponential model n of t is equal to n naught times e to the power of rt for the population t years after 2010. So for the population for after 2010, you have to find out what would be the what would be the model. So what is the data that we have? We have the rate of change, sorry, rate of growth, correct? Relative rate of growth with respect to time, and we have that the population at 2010 is 12 million. So substituting whatever data we have in the equation or in the given model that is being defined, so we get n of t to be equal to, so 12 million, correct? So we can initiate, or we can graph it in terms of millions itself. So I will consider it to be 12 million times e to the power of 1.2% is nothing but 0.012 in decimals times t. So this would be our model. Okay, so now the second question is, estimate the fish population in the year 2015. That is, what in 2015, what is n of t? N of t is how much, like what is the population of the fish? So n of t is equal to 12 times, so 2010 to 2015 will be 5 years, right? So e to the power of 0.012 times 5. So this would be, if you use a calculator, so e to the power of, I'm using it, you can do it along with me, 0.012 times 5 would give us something like 1.0618, okay, times 12, is 12.7420. So this times, because it is, you have to express that in millions. So okay, I'll go back. Yeah, so this would be 12.7420 millions. Or if you have to write it as a whole number, so this times 1 million, sorry, yeah, 1 million would be 12742038. So 0.58, you have 0.58, but this should not be considered because number of fish cannot be in decimals. So approximately as a whole number, it would be 12,074,200 and I'm sorry, it is yeah, it's more, it's it's more than like 12 million 742,038, correct? So this would be the number of fishes. So make sure you write the unit, or what the number is representing, if it is representing anything, so as soon after you express it as an answer. Okay, so the next one is C. Part C of the problem says, after how many years will the fish population reach 14 million? So you have to calculate if n of t is 14 million. Okay, so what is t, correct? So to substitute that, 14 is equal to 12 times e to the power of 0.012 t. So 14 divided by 12 is equal to e to the power of 0.012 t, correct? So 14 by 12 is something like 7 by 6 is equal to e to the power of 0.012 t. So taking log on both the sides, yes, so that implies log of e to the power of, or ln of, correct? Okay, it's okay. Log e of 0.012 t is equal to log of 7 by 6. So that would be 0.012 times t log of e is equal to log of 7 by 6. So this would be nothing but t is equal to log of 7 over 6 divided by log of e times 0.012, correct? I will use a calculator to solve this. The numerator would be approximately 0.66 or 67, okay, divided by denominator will be log e times 0.012. So this would be 5.2153 times 10 to the power of -3. So that's in the denominator. So yeah, so that would be okay, I missed the track. So yeah, log 7 divided by 6 divided by log of e times 0.012, correct? So this would be okay. So this would be approximately 12.8459. So 12.8459. The time is here years, right? So this would be years. The unit for this answer is years. So now sketch a graph of the fish population. So you have to sketch the graph. That in the sense you have to just plot the graph of the model that is given here. So that is n of this one. So let us do it using a calculator, graphing calculator. Okay, so that would be y is equal to, where n of t is y, and n naught was initial population was, what was the initial population? 12 times e to the power of point 0.012 x, correct? So let us see. Yeah, here is the population. So this would be the graph of the function. So you can see a clear exponential graph, right? So this definitely looks like an graph of an exponential function. Okay, yeah, so that would be the graph. You just have to write that or plot that or attach that in your answer. You can attach a picture, or you can even draw it based on according to the given data here. So where you can see the graph, so you can draw things like this. Okay, so that would be the answer. So moving further, I told you in the beginning of the video that we use this for comparing different rates of population also. So we shall do a problem based on that. I will do an example itself for you and explain. So the example says that in 2000 the population of the world was so this is example 4 in your book. So in 2000, if you have the population of the world to be is 6.1 billion, okay, and relative rate of growth, so that is R is 1.4% per year. It is claimed that a rate of 1% per year would make a significant difference in the total population in just a few decades. So we have to test this claim by estimating the population of the world in the year 2050 using a relative rate of growth. First one would be 1.4% per year, and B would be 1% per year. So that is compare the population at each rate of growth, okay, and see whether the claim that they say, like there would be a substantial or a significant difference in total population with just a few decades. So with a few decades or 20 years time down the lane, or 10 years down the lane, you can see just with 1% change in the rate of growth, you can see a very high increase in the population. So that is what your exponential model actually gives you, right? Okay, so we have to check whether the claim is true or not. And we should also graph the population for the next 100 years for these two relative growth rates in the same viewing rectangle. So we will do that. So first one, by the exponential growth model, we have n of t to be equal to 6.1 e to the power of 0.014 t, correct? So where n of t is measured in billions, you did not write the billion because it looks like too huge, so you can write it in billions, yeah. And t is measured in years since 2000. So because the year 2050 is 50 years, so 2002 2050 would be 50 years of duration, correct? So after 2000 we find n of 50 to be equal to 6.1 e to the power of 0.014. T is also 50. So this would be approximately be 12.3 billion. Okay, 12.3 billion. So the estimated population in the year 2050 is 12.3 billion. Okay, so now we will do for the other rate, that is 1%. Okay, so for 1% it would be n of t is 6.1 e to the power of 0.01 t, correct? So now n of 50 will be 6.1 e to the power of 0.01 times 50. So that would be approximately 10.1 billion. So you can see that there is a very high increase of 2 billion population just with the change of 0.4 percent rate of growth change. So and if you plot the graph for both the functions, okay, so we get y is equal to 6.1 times e to the power of 0.014 x. So this is one equation, and the other one is y is equal to 6.1 times e to the power of 0.01 x. So this is the two graphs. The red graph is the okay. So if you see the population like for 0 to 100, okay, the rectangle 0 to 100 will show you how the population is changing. The blue line is for 1.4%, and the red line is for 0.1%. That is 1%. Okay, so this is for 1.4%, and this is for 1%. Okay, so you can see that with the rectangle of 0 to 100, the graph looks like this. Yeah, so the graph looks like this. So this is the rectangle from 0 to 100. Okay, so that this example has been given in your previous in the book. I'm sorry, in the book it has been given, the same graph has been given in the same rectangle. So you can see the large difference in the population size, correct? So the two graphs are showing you that there is a huge difference in the population size. As you move further, you can see how much wide this particular two graphs can be if you for a small change in the input values. Okay, so and moving further, expressing a model in terms of E. So if you have to, we will learn about expressing a model in terms of E. Okay, so if a culture starts This is example 5 in your book. So if a culture starts with 10,000 bacteria, so that means initial number of bacteria is 10,000, and number doubles for every 40 minutes. So doubling time, that is your A, would be 40 minutes. Correct? So now you have to find a function that models the number of bacteria after t hours. So we have to use the doubling time here. So yeah, the model where we used base 2. So n of 2 is in the previous video. N of 2 is equal to n naught times 2 to the power of t over A. So that models the number of bacteria after t hours, and B would be after t hours for the given data would be 10,000. Sorry, n of t is equal to 10,000 2 to the power of t by so t by 40 minutes for 1 hour will be 2/3 of an hour. Correct? So it would be 2/3 of an hour. So I will write this as 2t by 3 in the power. Okay. So and the second function, or the second problem would be find a function n of t. You have to find it in terms of exponential in the expressing the given model. This is a doubling time model where we are using base 2, and we will use a model where we use base e. So n of t is equal to n naught times e to the power of rt. That models the number of bacteria after t hours. So we have to find such a model. So the initial population is 10,000. So that is given, and we have to find the relative growth rate r. Correct? To establish the doubling time model as an relative growth rate model. So that would be since there are for 40 minutes, that is 2/3 of an hour, you will have 20,000 as a bacteria, 20,000 number of bacteria, right? So because that is the doubling time. So t will be 2 by 3 of an hour. Correct? So yeah, it's just h. Okay, and for n of t will be 20,000. So substitute the given values in the equation and find out what would be r. So 20,000 is equal to 10,000 times e to the power of r into 2 by 3 t. Correct? 2 by 3 of 1 hour. So that would be just 2 by 3. Correct? So now solving for e, we get 2 is equal to e to the power of 2r by 3. Correct? Now applying log on both the sides. You can take log or you can take ln, because ln will cancel out the bases. So ln of 2 is equal to ln of e to the power of 2r by 3. Correct? So this implies ln of 2 is equal to r times 2r by 3 itself, because base e and base e, applying one of the property of logarithms, you get this. So r will be equal to ln of 2 times 3 divided by 2 is r. So that would be approximately 1.0397. So now we know that what is r, and we know what would be the initial time. So to write the model, we will be writing it as n of t is equal to 10,000, correct, in times e to the power of 1.0397 t. So this is actually the exponential, the model in terms of e. So you can convert the doubling time model with suitable data that is given into a relative growth rate model. You can convert a base 2 model to a base e model in this way. So now it's time for your quiz. Quiz 4.6.2. Solve problem number 8 and problem number 10. And one more would be problem 12. Okay, so this would give us the this would be the quiz for the second video, 4.6.2. Okay, so with this I'll end this video, and in the next video we will learn about modeling radioactive decay. Okay, we will learn how to model radioactive decay, also how to solve it, and we will see how logarithm or exponential functions or exponential models are used for actual scientific phenomena of radioactive decay. See you soon. Thank you for listening.